And what I did was not exactly proved, but sort of described the way in which one can prove a sample complexity estimate for a probability of the supremum of f in f of E mu f minus E mu n f greater than epsilon less than delta for classes of functions for which you have some sort of control on their empirical covering numbers. So one such example was VC classes. Another example was classes for which you have some knowledge on the fat chattering dimension. And what I mentioned at the end is that you can show by using the connections between the covering numbers, the empirical covering numbers, and the fat chattering dimension, is that if the fat chattering dimension is of the order of epsilon minus p, then the n you need here to ensure that this is greater than epsilon with probability less than delta, you need n to be of the order greater or equal than some absolute constant times 1 over epsilon to the power 2 plus p, and here you have logarithmic factors. Okay, so here you have a logarithmic factor in 1 over epsilon, a logarithmic factor in 1 over delta, and I'm going to ignore those. So in some sense, the rates by which things, sort of the sample sizes you need to take is something like epsilon to the power 2, which we knew to start with the absolute minimum for this approach, and you multiply it by 1 over epsilon to the power p, which comes from here. Now, the problem is that when people, yes?
What is the three brackets there?
Just logarithmic factors in 1 over epsilon and 1 over delta. Okay, so you have log squared, I think it's something like log squared 1 over epsilon plus log 1 over delta, something like that. Now, the only problem is when people actually run experiments to see if this is the case, it turned out that they needed a much smaller sample size. So you didn't need as many points as this to ensure that this happened. It happened much before that. And that was no big surprise because we expected this bound to be loose because we used the union bound. Okay? So the question was, how do you handle something like this in a different way? And that was a question which was open for many years until, like a lot of other questions, a guy named Michel Talleyrand solved it. Now, for those who don't know, Talleyrand is probably the greatest living probabilist today. He solved, he wrote hundreds of papers, solved hundreds of open problems. And this is one of them. So, first of all, I want to describe the idea. There's some fundamental idea behind his solution. I will call this random variable. I'll denote it by z. So Zn is the supremum of f in f, the expectation u in f. And here, just to show you on what this random variable depends, I will write the empirical expectation as 1 over n sum f at xi, which is exactly the same. Okay? So this is a positive random variable, and the claim that we have here, formulated in a sort of language of probabilists, means that the sequence Zn of random variables converges to 0 with probability, which is exactly the same as saying that the probability that this random variable is greater than epsilon tends to 0 as you take n to infinity, which is exactly what we have here. Okay? So if this happens, if this is 0, and you take an epsilon, one-sided epsilon neighborhood of 0, then you know that if you are if your n is large enough, then with high probability you would land here. Okay, that's all that it means. Now, the question was, so the idea was to see whether you can replace Zn by numbers. Okay, let's call them small zn's. Okay, for every n a small zn, with the following property. Zn is a number, and if you look at a small neighborhood of Zn, the probability that this random variable exceeds this neighborhood is very, very small. So if you want to think of it, think of a Gaussian random variable. And you know that Gaussian random variables are very well concentrated next to their mean value. So the definition of a Gaussian variable tells you that if you look at the neighborhood of its mean, then the probability that you exceed this neighborhood is really, really small. It decays exponentially. Okay? So the question was, can you have some sort of a result like this? Can you find, for every such random variable, can you find a number for which, if you take a neighborhood of it, the probability of being outside this neighborhood decays very quickly? Okay? Now, let's assume we can do that. Then the problem now changes. You have, instead of trying to handle this random variable, all you have to do is to see the way these numbers behave. If the rate by which these numbers converge to zero, in some sense, determines the behavior of everything. Because if these converge to zero quick enough, right, and you know that the probability that you're outside of these numbers decays very fast, then you get the sort of control we want. Okay? So the question is, can you find such numbers? And can you ensure that the probability that these random variables are far away from these values decays very, very quickly? Now that's the idea behind this is called the concentration inequality. So a concentration result means that with very, very high probability, the value of a random variable is a number, and that number is usually its expectation. Okay? So the idea is to show that, where is this? Yeah. That the probability that a random variable exceeds its expectation is very small. Now, of course, you have to make precise what it means being small. Okay? But that's the main idea. And concentration inequalities have played a huge role in modern mathematics. So over the last 30 years, they have been used in geometry, combinatorics, of course, probability, to solve also all sorts of open problems, because they simply reduce a very complicated problem of controlling a random variable to controlling a number. That's what we're trying to do. And what Telegram did was to show that this random variable is very well concentrated near its expectation. So Telegram's result, and I'm not going to present it in the way he presented it because it's very complicated, and since he published it, I think he published it in 1993, it had some improvements, especially in the constants, and certainly in the presentation by several others. I'll mention a few. Ledoux did some work in that direction. Pascal Massad, Rio, who was a student of Massad, and recently Olivier Bousquet also currently has the best version of this result. But essentially the result is the following. So let Zn be this random variable. Let sigma squared be the supremum of f in f of sum I equals 1 to n the variance of f of x. This is just the expectation of f squared. Okay, the variance. Okay? B is the supremum over f of the L infinity norm of f, which simply says in our case, so this means the largest value a member of your class can take. In our case, it's 1, okay, because all the functions are bounded by 1. So that's all I need. And the claim is, and this isn't the optimal claim, you can improve it in the constants, but that's all I'll need. Is that for every x greater than 0, there is a set, before that, there is an absolute constant C such that for every x greater than 0, there is a set of probability larger than 1 minus e to the power minus x, on which this random variable z for every n, okay, so that's omits the n, is less or equal than twice the expectation of z plus the absolute constant. I'll just make sure I'm not making any mistake. Sigma square root of x plus bx. So, and you can specify this c, which is a small number, and you can improve this to something which is arbitrarily close to 1. Now, let's analyze this before we continue. This means, first of all, that you have a very good decay. Okay? Things decay quickly. The probability that this doesn't happen is decays exponentially, which is a thing you would like. And this tells you that z is smaller than not its expectation here, but twice its expectation, plus something which we hope to make small. Okay? The question is, of course, how do you select x and how do you select n to ensure that this is small? Okay? But the idea would be that the dominating term in the behavior of this random variable, excluding a very, very small set, is this. Okay? And this is where I'm reducing a probabilistic problem of estimating something to estimating a number, the expectation of this random variable. So let me just give you one example on a way in which you can control this. Okay? Yes?
Confused by the definition of sigma squared b. Where's the I? That's just a number.
No, it's a function. Remember, x is you sample your space. Right? So every value of x, you get a member of your domain omega, and f at that value is a number, right? So this is a random variable. Okay, let me just remove this. Okay. So let me give you an example. In our case, we know that we can take b equals 1 because all of the functions are bounded by 1. Okay? What can I say about sigma squared? F is bounded by 1, so f squared is bounded by 1, so the expectation of f squared is bounded by 1. So here I'm summing, and this is true for every f in your class. So now I'm summing n things which are smaller than 1, so sigma squared is smaller than n, so sigma is smaller than the square root of n. Okay? Oh, I'm sorry, I made a huge mistake. Forgive me. Change the definition of z. Huge mistake. That's the way it should be defined. So it's sum equal 1 to n f at xi minus the expectation of f. So the difference, which makes all the difference in the world, is the normalization, right? The difference between the former definition of z and this one is the normalization by 1 over n. So this is n times larger than what I had before. Makes every difference in the world. And you'll see in a minute. You'll see in a minute where. So let's write what we have using this. Okay, let's write what we have this. So I want to do, how do I go from this z to the one we usually have? I do it by dividing by n. So I want to divide both sides of the equation by n. So z over n is simply supremum of f in f, and now it will be 1 over n sum of f at xi minus the expectation of f, and this is exactly the random variable I'm interested in. Okay? So what we have is that z over n, let's call it y. So what we have is y is less or equal than twice the expectation of y plus c over n. And now we have sigma is less than square root of n, so square root of n, square root of x, plus x. Okay? Now I want to specify the choice of x. Okay? So the x I'm going to select, this is true for every x, so I'm going to select a very special x. I'm going to select x to be equal, so n epsilon squared divided by 4c squared. I did this. Now if you plug that in, you get that with probability, let's do it here. So you get it that with probability greater than 1 minus e to the power minus x, so this is minus n epsilon squared divided by 4c squared, you have that y is less than or equal than 2 the expectation of y. And when you plug this definition of x, okay, the square root and the square root kill each other. And from here, if I did the calculations correctly, I believe I did, I'm not sure, you get 3 over 4 times epsilon. Okay? Just plug x here. Okay? Now, remember what we want, so let me write this explicitly. It's supremum of f in f, the expectation mu of f minus e mu n of f is less than or equal than twice the expectation of the supremum of f in f of the same thing plus 3 over 4 epsilon, and this holds with this probability. Okay, yes? Problem? No? Okay, so remember what I wanted to estimate is that the probability that this is greater than epsilon, okay, is smaller than delta. So if I can ensure that this is smaller than a quarter epsilon, or maybe an eighth epsilon, right? I know that this would be smaller than epsilon with this probability. Okay? So the complement being larger than epsilon will happen with this probability. Okay? So set this to log 1 over delta. So if you take n epsilon over 4c squared equal epsilon squared, right, log 1 over delta, and if the expectation of the supremum of f in f of e mu f minus e mu nf is smaller than epsilon over 8, this would imply that the probability that the supremum of f in f of e mu nf, or mu f minus e mu nf greater or equal than epsilon is smaller than delta. That is just rewriting this. Okay?
Not your question. I think you require that epsilon is less than c.
Pardon?
You do require that epsilon less than c.
No, I don't think so.
Otherwise, you're inequality.
Otherwise,
You're inequality with 3/4 epsilon.
Oh yeah, you assume that c is better than 1. I always assume that my constants are greater than 1 and epsilon is between 0 and 1. Of course, you're right. I didn't understand what you're saying. Sorry. Okay. Yeah. When I say an absolute constant c, I always mean an absolute constant greater or equal than 1. So now from this, we can have a sample complexity estimate, right? Almost. A sample complexity estimate, maybe want to make sure I didn't make any mistake. Yeah, that's fine. Okay. And the sample complexity estimate is composed of two terms. The first one is controlled by this. So n needs to be of the order of log 1 over delta times epsilon squared. 1 over epsilon squared, I mean. So this means that you need n to be greater or equal than c over epsilon squared, a different c, log 1 over delta. Which is exactly the same kind of condition we had to use for the symmetrization argument. This is exactly the kind of constraint we had. Okay? So this is, in a sense, and in fact, the best you can hope for to get such an argument. I haven't proved it, but I'm telling you that to get this kind of a deviation estimate, you would need at least this number of samples. So this is the absolute minimum. You might, improve the C, but rate-wise, this is the best you can hope for. So the question is, how much worse will you have to? I mean, how many more examples will you have to see? And that only depends on this. On the way that the expectation of this random variable is comparable with epsilon, or something proportional to epsilon. Now, people looking at this might say, okay, our situation hasn't improved by much. I didn't know how to handle the probability, but now I don't know how to handle the expectation. Right? The expectation, how do you control something like this? And that's exactly where the Rademacher averages come into the game. The Rademacher averages, which I'm going to define in a minute, are a way of controlling this quantity. So let me just define this. So definition. Rn of class F, and I write Rn of F, but it isn't Rn of F. It depends also on the probability measure according to which you're sampling, but I'm not going to use that. I'm going to omit this notation. It is defined as, and now, okay, I'm going to write it first, 1 over square root of n, the expectation with respect to x, the expectation with respect to epsilon, supremum of f in f, sum epsilon I f of xi, where xi are IID distributed according to the probability measure mu defined on your space, and epsilon I are independent Rademacher random variables that is symmetric minus 1, 1 valued. Yes?
So what's the expectation over?
The expectation, okay, write this, it's a good question. I'll write this in a different way, okay? I'll write this as the supremum of, yeah, this is the randomness. This is just a number, and this is just a way of writing 1 over n sum f at xi. Okay, so this is a random variable depending on the xi's, and now we take the expectation with respect to that. Okay? So this is the way I define the Rademacher complexities, or Rademacher averages associated with a class, and there's a big argument between me and a few other people about the proper way of defining this. You may see sometimes this term normalized in a different way by 1 over n, or even without a normalization. Okay? But that's the way I like it. So you'll have to suffer because I'm presenting the talks. No, there's a reason behind this. It's not just, an arbitrary decision. So the important fact is, and this is a version, sort of an averaged version of the symmetrization argument that was used to prove this old type bound, you can show that Rn of f, in fact, control this expectation. And I'm only going to use one direction of the inequality, but you're going to get the reverse inequality as well. So this is a theorem which says that the expectation of the supremum of f in f, the usual stuff over there, is bounded by twice Rn of f over square root of n. Okay? So in fact you can get something very similar which depends differently on. So if you want to control this, it's enough to control this. Okay? And using this and what I wrote over here, you get the following sample complexity result. So, corollary, the probability that the supremum of f in f greater than epsilon s equal than delta, provided that n is greater than equal than some absolute constant which doesn't depend on anything, of course, the maximum between two terms, Rn squared of f over epsilon squared and log 1 over delta over epsilon squared. Okay, you can just do the arithmetic and see if I've cheated or not. I think I haven't. Okay, so this is the best you can hope for, and how much more you have to sample depends on this, on the way that your Rademacher averages behave as a function of n. Now, of course, this depends on n. It might increase with n, giving you a condition on, so you'll have to solve the equation. If this grows too quickly with n, I mean, if Rn of f goes quicker than square root of n, then the bound doesn't work, right? Then you can't show anything. So square root of n seems to be sort of the borderline case. If your Rademacher averages grow quicker than square root of n, you can't do anything. If they grow slower than square root of n, you can do something, and in fact it's true. So square root of n is exactly the border rate. If you have a rate which is better than square root of n, you have a uniform Blivenko-Cantelli condition. If your rate grows faster than that, you don't have uniform Blivenko-Cantelli condition. So this is the breaking case. Yes?
You say that what you just circled is like an absolute minimum.
Yes, I haven't proved that.
But, yeah, okay.
I haven't proved that, but it's true. It's the absolute minimum for, you have to be careful. It's the absolute minimum for this kind of an estimate. Okay? It's not the absolute minimum for sample complexity of a learning problem. Right? Remember, this is just an upper bound for the sample complexity of a learning problem. You can improve that for a learning problem. Okay. Again, people might look at this and say, interesting result, we haven't improved by much because I don't know how to compute the Rademacher complexities of a class. I don't know how to show, I can't compare, for example, this result to results using the VCD dimension or the fat chattering dimension, because how do you compare two such strange objects? What's the connection between the two? So there are several ways in which one can compute the Rademacher complexities. And I'm just going to start with one. Maybe I'll show more. I'm just going to start with one. And the one that connects the Rademacher complexities and the covering numbers. Okay? I'm always whispering. So, Rademacher edges and covering. Yes?
Now you know that the looseness of the union bound anymore. Can you comment a bit? What do you think which of the steps are the most loose, even though they are much tighter?
Where? Here?
Yeah.
Okay. The results, in a sense, in my opinion, are as loose as you can get. You're not losing much except constants. Yes, because of the following reasons. I think it's tight. First of all, it's tight because I can prove that if your class is sufficiently large, then you get a tight estimate. So that I can prove, so there is no argument there. For smaller classes, it's not so clear. But again, I believe that, you can claim that the complexity estimates you get in this result, when you try to measure them according to, for example, the fat chattering dimension, you get the best possible bound. Okay? But if you want a deeper sort of argument, this Tyler-Grens inequality, is a great thing about it, and I'm going to talk about this in my last lecture, is the fact that it's an analogous result to the Bernstein's inequality. So in these lectures, I've only mentioned Hoeffding's inequality, where Hoeffding's inequality is simply a concentration result for a single function, and your bound, your exponent, the decay rate, depends only on the L infinity norm of the function involved. Of course, if you know something more about the function, you can get a better rate of decay. So if you know something about its variance, you can get a better result. And that's where Bernstein's inequality or Bennett's inequality came to. I mean, they tried to solve this problem, and the bounds there seem to be tight. I think you can show that they're tight. Tyler-Grens result is a functional inequality of that type. It's a functional Bernstein inequality, and if you know something about the way the variance of the class behaves, okay, then you get a better bound. You see, here I only use the fact that my functions are all bounded by 1 to estimate the variance, but if I know a bit more, I get a better bound. Now, if you take Tyler-Grens inequality to the trivial case of a single function, you recover Bennett's inequality. So in that sense, I don't think you can prove this step. The other step, you can just prove that the expectation is controlled from above and below by the same quantity, so it has to be tight up to the constants involved. Right. So Rademacher averages and entropy. The way I've defined them, you can do the same trick I did after symmetrization. What I did in the first proof, I symmetrized, then I conditioned on the sample. And I can do the same thing here. I can, instead of looking at this kind of Rademacher average, I can look at a sample-dependent version. So if you fix a sample, Sn, which is x1 to xn, you can look at 1 over square root of n, the expectation with respect to the Rademacher averages, the supremum of f in f, some epsilon I f at xi. So this is a sample-dependent version. Let's call it R of f modulo Sn. Now, to get Rn from this, all you have to do is to integrate with respect to these. And that's where the probability measure according to which you do the sampling comes into the game. Okay? But this becomes a completely deterministic problem, right? You have these vectors, f at xi, which are elements of Rn, and you want to compute this expectation. Now, the reason things work so well, and that's the reason I chose this normalization, is because of the following very beautiful result of Dudley. He first proved it for Gaussian variables instead of the Rademacher ones, but you can prove it for Rademachers as well. He proved the following. That's Dudley. There exists an absolute constant with the following property. 1 over square root of n, the expectation of epsilon, supremum of f in f, sum epsilon I f at xi is less or equal than that absolute constant times the integral between 0 and infinity square root of log n epsilon f L2 mu n d epsilon, where mu n is the empirical measure supported on the xi's. So what you do in some sense, you take your function class, you look at a fixed sample. In some sense, you project everything into this space, L2 mu n. Now the question that you have here is computing the quantity which involved averaging vectors in that space. And you take the expectation of this, you normalize it by this way, and this is bounded by an entropy integral. So this is a very, very nice result. I'm not going to prove it. Like most of the results here, I'm not going to prove. But now, since I know this, at least in some cases, I can compute the Rademacher averages in terms of the combinatorial parameters, the VC dimension and the fat chattering dimension, because I know how to bound the covering numbers in terms of these parameters. So let's start with the VC dimension. Maybe we'll have a break before I start with the VC dimension. So let's have a 5-minute break.